Okay, fine. We were here. Okay, fine. We were here in the last class. So we saw how to find the maximum from the collection of element, or the maximum element from the given n numbers. Now, the next thing is, let us next problem we are trying to solve is sorting a collection, or from among the n numbers, we will need to sort these numbers into ascending or descending order. Usually when we say sorting, what happens is we will be sorting according to ascending order. That is by default. Now, this much more. Now, this problem, if you can generalize it, a simple solution will be from the elements that are unsorted. Remember, from the elements that are unsorted, find the smallest element and place it in the sorted list. Now, this is a way general form. It's a very simple solution, but doesn't say where the elements are stored, how many number of elements are there, or that doesn't tell us the internal details or minute details or basic steps of an algorithm. So let us look at the algorithm. This is known, the very first step is for us to examine, starting from the first element till the last element. That is n in this case is 5, because we have 5 elements. So we start from the first element, move on to the last element, and sort the collection, that is sort the n numbers. Now, to move from starting from first element till the last element, we use a for loop for I 1 to n, that is from first index to the last index. Now remember, here in most of the high level programming languages, what we say is the index of the array starts from 0. But this is not this is a pseudocode. It's for the algorithm. It's not concerned about any of the high level programming language. So in pseudocode code or in algorithms, we assume that the array index starts from 1 till the n elements. So we have for I 1 to n and examine all the elements from ai to an. Then we have to pick up a smallest element, that we will assume that it is in the jth index, that is it's at a of j. Then we have to interchange the element that is in the first position, because I is 1 right now, from the element which is at the jth position. So these are the basic steps what we have, but still this is not an algorithm. Now, for an algorithm, we need to have steps in pseudocode that is understood by a computer. So let us look at how do we can translate that. Obviously, this for loop is going to be as it is, and then that is for I equal to 1 to n. Then this part is first task that has to be accomplished, and then interchanging the elements is the next task. The first task is to move from the elements and choose the smallest elements among the elements which are unsorted. And the second task is to interchange. The second task is very much easy. It doesn't take any logic as such. Just have to exchange 2 elements, or just have to swap 2 elements. Now, this part can be done using a temporary variable t and assigning the value of a of I, Then to that A of I assigning the value of A of j, and then A of j assigning the value of the temporary stored value, that is t. The second task, the first task, it's a little bit complicated. And here, the very first thing is we will use a variable as j, that is for the index. So j will be initialized to I. Then this part j will be initialized to I. Then we will have a for loop start with the index as k. So k will start from somewhere, I plus 1 till, and then we compare and swap the indices. Now, if you look at the actual working of this, what happened was, just a minute, the whole thing got stuck. Come on now. Okay, now let us talk about this part for loop or the task one. Now, what actually happens is this task one, the very first statement we have is I, because for I is initialized to 1, the I index. Then for this task, j is initialized to I. So I and j will be pointing to the same index. That is, initially I is pointing to 1, index 1. So j will also point to index 1. Then we have a for loop k, which starts from the next index. So I is 1, I is 1, even j is 1. K is going to start from I plus 1, that is 1 plus 1, which is second index. And it's going to go until the end m. Now, each time what we do is we compare if A of k, that is this 47 value, is less than A of j, that is 84. So this is obviously it's less. So what happens is we have to move j to the place of k. So k is 2, so j will be assigned index 2. Then this for loop continues. Next time k will be to n. We have to go till n. So k will be index 3. So k will move to index 3. Again, this if statement is checked. That is, if 21 A of k is less than A of j, that is 47. Yeah, it's true. It is less than 47. So j will again move. Then once again we are in a for loop. So k will move to the next location. That is, k will move to 96, element 96. And then if A of k, that is 96, is less than A of j, which is 21. This check, it is false. So k will not be assigned to j. That is, j will not move to kth index. It will not move. Then again we have a for loop. So for loop continues till the end last element. So here k moves. Now k is pointing to index 5. Then k is pointing to index 5. That is, if we have the if statement A of k, which is 15, is compared with less than 21. So this is true. So j will move to k. That is, k is fifth index. So j is assigned the fifth index. So it moves to the fifth index. Now at this point, k, this for loop has completed. So that is, for loop for k has completed. We reach the end of the the array, and now j is pointing to fifth element. And now we have to swap. What are we swiping? We are swiping A of I, which is 84, because I is index 1, so it's element 84, is swapped with element 15, that is A of j. So these two elements are swapped. So we found this for loop, using this for loop, we found the smallest element among the unsorted elements. And that is getting replaced with the first element. So the whole algorithm, if you see these steps, the entire steps of these algorithms, that is two tasks. That is, one task is to examine all the elements and then choose the smallest element at some place A of j, where j is the index, and replace that, swap that element with the first element for the first iteration. So this becomes an algorithm, and this algorithm is very popularly known as a selection sort algorithm, because for loop, in the first stage, for loop, we start with I, that is the first I, the first round we say, we start from the first element, find the smallest element and place it, selects actually the smallest element, place it in its place. Then this for loop will again execute with when I equal to 2, that is I will start from the second element, and again same procedure continues, j will be pointing to the second, k will start from the third element, this continues. So this is known as selection sort algorithm. So this way, we last class we have just seen a simple algorithm of finding the maximum element, and in this session we have seen how to perform a sorting, which is a simple sorting method we have seen known as selection sort. Now, why are we seeing these examples? Because to have an idea about how the algorithms are, or how the algorithms are written. It's not written in high-level language. They are written in pseudocode, and the statements are almost same as the high-level language. But this is how we are going to have the algorithm. And throughout this subject, when we move further, we will be analyzing these algorithms and knowing its complexity, or knowing actually trying to find its performance. So now let's move on to the next topic. The next topic is another type of algorithms known as recursive algorithms. Now, till now what we have seen is an algorithm which performs some task and completes its execution. Now, like we have recursive functions, that is a function calling itself, the same way we have recursive algorithms. Recursive algorithms also calls itself within its body or from within its body. So recursive algorithms same as functions, recursive functions. Now there are two types of recursions here. One is known as the direct recursion. In the direct recursion, we have an algorithm A, and this algorithm is called within its body. The same algorithm is called within its body. So this type of recursion is known as direct recursion. Then we have another type of recursion known as indirect recursion. In the indirect recursion, we have one algorithm, which is algorithm A, in this case, as an example. And this algorithm has a call to some other algorithm known as B, algorithm B. And algorithm B, there is another algorithm B, which we are trying to make a call to, algorithm B. This algorithm makes a call to algorithm A again. So what happens is we have an algorithm A, and in algorithm A, there is a call to another algorithm B, known as B, algorithm B. And that algorithm B has a call to again algorithm A. So this actually forms a cycle. So this is known as indirect recursion. So broadly speaking, there are two types of recursions known as direct recursion and indirect recursion. This is broadly speaking, though there's even in direct recursion, we have several other subtypes known as, for example, tail recursion, head recursion, and tree recursion. So, but broadly speaking, we have something known as direct recursion and indirect recursion. Now, for recursion to work, let us take a basic template of a recursion. Now, here we have algorithm, and that algorithm is nothing but, let's call that name of the algorithm as function 1. It may or may not have parameters. So, algorithm may or may not have parameters. Then we have certain condition statements here, followed by a if statement with a base condition. Now, this if statement with a base condition is nothing but, remember that every recursion, or in every recursion, there should be a base condition which tells us when to stop the recursive calls. Otherwise, it will just be like an infinite loop, or we will be entering into an infinite loop. Recursion will not stop at any point of time if you don't have a base condition. So there should be a base case or base condition through which the recursion or a call to recursive function is not executed. So that is one very important point. And then within the base condition, we have a call to the algorithm itself or function itself. That is function making a call to itself. So always remember, in recursion, there should be a base condition or base case. If there is no base case, then we enter into an infinite recursion, infinite loop. So that is most important part. Now let us try to look at a classical example of recursion, that is factorial. Though it is not that it's only for factorial a recursion can be applied. Factorial is just a simple way to understand the logic of how recursion works. Factorial, we all know, it's in mathematically, it is, if we say n factorial, it's represented by n exclamation. And this n exclamation means n factorial, which is 1 multiplied by 2 multiplied by 3, 4, which goes on till n, because we are having n factorial. Now, in programming, let us call this as an algorithm factorial of n. So within brackets, we will just call this as factorial of n. Now, let us rewrite this equation. This factorial of n can be written as 1 multiplied by 2 multiplied by 3 multiplied by 4. Then instead of last term n, we will say multiplied by the third last term, that is n minus 1, multiplied by third last term is multiplied by n minus 2. Then second last term is multiplied by n minus 1. And the last term is multiplied by n. So we have not done anything new. What we just did is we have added a few more terms at the end. Few more terms at the end we have just added. That is n minus 2 multiplied by n minus 1 multiplied by n. Now here, if you see or if you look, this part is nothing but it's factorial of n minus 1. So if you look at this scenario, this entire thing till the second last term is nothing but factorial of n minus 1, because we are multiplying 1 multiplied by 2 till n minus 1 term. So this becomes n factorial of n minus 1 if we mathematically look at the terms. So factorial of n is nothing but, if we say it's factorial of n minus 1, then the last term what we have is multiplied by n. So if you look at this relation or this expression, for factorial of n, what we have is factorial of n minus 1 multiplied by n. So this gives us some kind of a recursive formula. Now, you all know factorial, before we look at that recursive formula, you all know that factorial of 5 is nothing but 1 multiplied by 2 multiplied by 3 multiplied by 4 multiplied by 5, which is nothing but equal to 120. Now, let us look at how to arrive at this equation of recursion, or using this equation, let us look at how we arrive at the recursive algorithm. Now, before we derive the relationship, let us say we have factorial of 5. You can compute factorial of 4, factorial of 3, factorial of 2. But what about factorial of 1? factorial of 1 will be 1 itself. Then what about factorial of 0? Factorial of 0 is also mathematically 1 itself. We are not going to go into negative terms and all, but let us say factorial of n will be factorial of n minus 1 multiplied by n when n is greater than 1. When n is greater than 1. And then when n is equal to 1, that is factorial of 1 will be 1. That is when if n is less than equal to 1. So we are not going to go for minus negative factorials, but we need to arrive at a condition where there is no factorial or recursive call. So that is why we are taking if n is equal to greater than n is greater than 1, then it is factorial of n minus 1 multiplied by n. If n is equal to 1, or let's say n 0, so we say n less than equal to 1, it is 1. Now, how do we write a factorial algorithm using this relation? So mathematically, we have arrived at the relation where, depending upon the value of n, we can evaluate the expressions. So what we say is, let us call this function as factorial of n itself. The name of the function itself, factorial, pass n as the parameter. That is what we have it here. First, we need to handle the base case. That is this one. If n less than equal to 1, that is if n less than equal to 1, then we return 1. That is the result answer. Factorial of 1 is 1 itself. So if n is equal to 1, we return 1. Else, we have the second part. Else, if obviously if this is false, that means n is greater than 1. So we return same this factorial, that is this is the function factorial. Recursively we are calling factorial function factorial n minus 1 multiplied by n. So what is happening here? We have converted this mathematical expression with the condition. So this forms our base condition, that is if n is less than equal to 1, then there is no need to recursively call the factorial function. Just simply return 1. So this n less than equal to 1 becomes our base case or base condition. And if n is greater than 1, then we are calling factorial recursively passing n minus 1. And obviously this multiplied by n will give us the result. So this is a classic example of how recursive algorithms work or how we formulate recursive algorithms. Now, this kind of relationship, what we have found using this last second till the second last term and using the last term, and found this equation, which we have some result for some value of n and some other result for some other value of n. So this part is going to be, is a very important part, because when we analyze for the performance or when we move further with divide and conquer approach, we will be having such kind of a relationship. So that is why what we have seen a very basic example of a factorial function with respect or factorial algorithm. Then let us move further of another classical example of factorial. It's known as Tower of Hanoi problem. So in your data structures, if you have heard about or have seen, you may have just solved this problem, or you may have had a program to write a Tower of Hanoi, or by-hearted this function and written it. But let us try to look into the details of what this Tower of Hanoi problem or puzzle is, and how we arrive at a recursive function for this Tower of Hanoi problem. Now, this is a classical problem, an ancient problem, where we have a tower, which the legends call it as a diamond tower. Let us call this tower A, with 64 discs. There are 64 discs, and these discs are arranged according to or stacked according to decreasing order from bottom to top. that is the largest disk is at the bottom, and smallest disk is at the top. This largest and smallest we are talking in terms of weight. They are heavy disks that we are talking in terms of weight. Then the legend or the ancient saying is that there are two more towers, Tower B and Tower C. These are also diamond towers, and these disks they say are golden disks. Golden disk. So anyway, let us call this towers as Tower B and Tower C. Then the problem or the what people or ancient priests are trying to do is they are attempting to move the disk from Tower A to Tower B using Tower C, that is the last Tower C, or it's not actually a Tower C, but there is some tower for intermediate storage. We call it as Tower C for intermediate storage. So every time you're going to have three towers, and you have to move disk from one tower to another tower with the help of an intermediate tower. Then there are certain conditions. That is, since the disks are very heavy, only one disk can be moved at a time. Cannot move two disks at a time. Only one disk can be moved at a time. And at no point of time, we can have a larger disk on top of the smaller disk. Always the disk has to be stacked according to decreasing order. That is, always larger disk should be below the smaller disk. So these are the things. Now, the actual problem to solve is that the entire content or disk from Tower A has to be moved to Tower C. And obviously, only one disk can be moved at a time. And when all the disks can move to Tower B, then and one, the heavier disk always has to be below the smaller disk. So then the problem is solved. Actually, it's a legendary problem that once the 64, they say that once the 64 disks are moved from one Tower A to Tower B, then the world will come to an end. So let us try to formulate an algorithm for this. Let us first see how we move these disks. And you have the conditions, that is, only one disk can be moved at a time, and the larger disk cannot be on top of smaller disk. So our problem is to move these three. Let us take an example of three disks. We are not going to take 64 disks. Just taking three disks to demonstrate how a recursive algorithm can be formulated. So here we have three towers, Tower A, B, and C. From Tower A, we have to move disk to Tower B using Tower C for intermediate storage. And we have three disks, green, yellow, and purple. Now, the solution would be to first move the green disk from Tower A to Tower B. Now, none of the conditions are violated. That is, we have moved only one disk at a time, and the larger disk is not on top of a smaller disk. The second move would be, so we will move yellow disk from Tower A to Tower C. Now, there is no conditions are violated, everything is fine. Then we will move the green disk from Tower B to Tower C. Now here, if you look at the stage, purpose was to move all the disks from Tower A, that is three disks from Tower A to Tower B, and once they are moved, they should be in same order. So at this stage, what we did is moved, actually using three steps, we moved two disks, that is green and yellow, to Tower C, and in that order. Obviously, we took three steps to do that, so in that order we moved. So when we moved in that, in that order, Tower B is empty. And now we can move the largest disk, that is the purple disk, from Tower A to Tower B. So to move the largest disk, that is, we have three disks. The largest is the third disk. To move the third disk, we had to move two disks, that is first and second disk, to tower C, and then move the largest disk. So if we have n disk, the problem is if we have n disk, then to move the nth disk, the last disk, we will be moving n minus 1 disks, several disks, n minus 1 disk to tower C, and then move the nth disk to tower B. Now, after this, what happens? Now let us try to formulate this algorithm, this problem of, because the largest disk is at its place. So now let us try to solve uh, moving these two disks. So let us say that now we have only two disks to move. Third disk is already moved. So nth disk already moved. Now we are, left out with two more disks. That is n minus 1 disk. So in this case, three disks, so only two disks. Now let us consider this as tower, instead of tower C, let us consider this as tower A. Why I'm saying tower A? Because if they are n disk, we have to move those n disks from tower A to tower B. Now to move those n disks, or to move the nth disk from tower A to tower B, we have to move n minus 1 disk from tower A to tower C. That is what we did with these three steps. Then move the largest disk. Now assume that these two disks are here at this place. So it becomes a problem of now moving n disk to tower B, but in this case, it's n minus 1 disk are left. So moving n minus 2 disk and then placing the n minus 1th disk. So for this, what we do is we move the green disk to tower A. So if we consider this as tower A, the tower C as tower A, and this as tower C, this step, fifth step, is same as what we did for step 1. So we move green disk to tower A. In this case, it is from tower C to tower A. That is what we are doing. So if we reverse this, makes this as tower C as tower A and tower A as tower C, the same step we did in the first step. Then move the largest disk, that is the yellow disk, from tower C to tower B. So if we consider again this as tower A, and this obviously is going to be tower B, this step will be same as moving yellow disk from tower A to, moving this, the third step, moving yellow disk from tower B to tower C. So it's actually, if we reverse it, we will moving that. And the last thing is, now we are left with only one disk. So now we can move green disk from tower A to tower B. So this way, using these 7 steps, without violating any conditions, we will be able to move all the disks from tower A to tower B. In this case, we only have 3 disks. Now, let us look at how this algorithm works. Let us take the 3 disk itself, and let us call this function as tower of Hanoi. And the first parameter we pass is number of disks. Second parameter is tower A. Third parameter is tower B, and fourth parameter is tower C. Now remember, always our problem is to move from tower A. Move the disk from tower A to tower B and use tower C for intermediate storage. So first tower is the tower where we have the disk. Second parameter, in this case, first parameter is the number of disks. Second parameter is the tower we have where we have the disk. Third parameter is the tower to which tower we will be moving. And third parameter is nothing but the tower for intermediate storage. That is in this case C, tower C. To solve this problem, I said that the last disk, if it's nth disk, this is n minus 2. So to solve this problem, we can solve it of tower of Hanoi of moving the two disks from tower A to tower C. So from tower A to tower C using tower B for as intermediate storage. Then once these two disks, that is green and yellow disks, is moved, these two disks are moved, then we will be able to move the largest disk, that in this case purple disk, to tower B. So we just say move disk. Obviously, it's only going to the largest disk from tower A to tower B. Then we have now, after this stage, after this moving two disks from tower A to C, B as the intermediate storage, these two disks are now tower C. So from tower C, we have to move it to tower B. So we will again call recursively tower of Hanoi, passing two disks because we only have two disks here. This disk are on tower C, and then we have to move it to tower B on the second tower using tower A as intermediate tower. So this is for three disks. Now, what about how to solve this tower of Hanoi for two disks? So if you look at two disk problem for tower of Hanoi, two disk, let us say A, B, and C. It doesn't matter which way we call these towers are, A, B, C. We can call it anyway. The only thing is from one tower, it has to be moved to the, all the disk has to be moved to the other tower. So when we have two disks moving from A to B and C, now what happens is move one disk. So that is moving only one, so first parameter is 1. Second parameter from tower A, we have to move it to tower C. That is what we have it here, tower C, and then to tower B as intermediate storage. Then from tower A to tower B, and lastly, we repeat the same steps. That is from one disk moving from C to B, tower B, using tower A as intermediate storage. What about these two? That is tower of Hanoi for one. How to solve? Now this is going to be the same way. One for one disk. A is the first tower. B is the tower where we are moving. C will be the tower used as intermediate. And then here we have used three disks. So to move three disks, we have to first move two disks. So here, if you have two disks, we have to move the first disk. One disk first. If you have one disk, we have to move zero disk. Though it doesn't work. There is no zero disk. You don't move zero disk. But once we have the same equation, we are having it, our same formula we are using, or same recursive call we are using, as well as the third statement, same recursive call we are using. Now the point of showing here that to move one disk, we have to first move zero disk is that to let you know what is the base condition. So here, if you look at this scenario, base condition is when they are disk, then we can recursively call the tower of Hanoi problem. But if there's zero disk, that means there is no movement. So there is no need for us to recursively call this algorithm. So if you look at the algorithm on the right hand side, we have tower of Hanoi algorithm. Here, when we are having three disks, we pass we recursively call the same algorithm for two disks. Over here as well as over here. Suppose if we have n number of disks. So here we are using the parameter as n. Tower A we have used as x, some variable x. Tower B we use some variable as y. And for tower C we use some variable as z. Then these recursive calls should go until n is 0. Till n is not 0. So we say that if n greater than equal to 1, then recursively called the tower of Hanoi. And we are using n minus 1 because for 3 we had to move two disks. For two disks we had to move one disk. So if there is n number of disks, we will be moving n minus 1 disk first, and then move the last disk. Then again perform the move the n minus 1 disk from the some tower C to tower A. So here, since we had A, which is for x, C is for z, and B is for y. The same way here we had C, B, and A. So C is for z, B is for y, and A is for x. So this is how we can devise a recursive algorithm for Tower of Hanoi. So, though we have not started analyzing anything, we are just trying to develop algorithms. So this is another type of a recursive algorithm. That is one we have seen as the factorial. The other one we have seen as the Tower of Hanoi problem. Now, the third is the permutation generator that I'm going to take up in the next class, or in the, obviously next week we're going to take up the other, the third thing, permutation generator, which we are going to take up in the next class. So we are still in the recursive functions or recursive algorithms. So if you have any questions before we end the class, let us clarify them, or else we can meet in the next class. So if there are any questions, just ask me, else we will end this class and this session. So I don't think so there are any other questions because people are leaving. So anyway, it doesn't matter. Thank you very much for this for attending this class. Let us meet in the next class. I request everyone to just log off.